In this video we are going to learn what containers actually are, and we are going to do this by first taking a look at how we would deploy applications or websites or whatever we have historically. So firstly we will take a look at bare metal, and then we will consider what a virtual machine is, and after that we are going to take a look at how Docker and containers in general compare to these two alternative methods. And of course we are going to review the benefits of containers over bare metal and virtual machines. And then finally we are going to wrap up and review everything we have just learned. So let's go ahead and get started by answering the question, what are containers? Containers are isolated execution environments in which you can run your commands or deploy your environments or set up your applications. Now before we explain how containers actually work, let's take a moment and look at how containers differ from the way we used to deploy things previously. So if you have any sort of technical background or you are familiar with the IT concept, then you may be familiar with the concept of bare metal, and this is when you take your application and deploy it directly on the actual server itself. And if it helps, you can think of this as your workstation computer, the physical computer that you are on right now. It's the actual physical computer that's there, and for bare metal there is no virtualization at all. So bare metal basically just means that you have your hardware, you have your CPU, you have your RAM, you have your physical server, and then you deploy your operating system directly on top of that server. After that, on the operating system you have all your prerequisite libraries and the things you need to deploy your application, and then you have your application itself, and it just sits on that computer and it's not isolated from anything else on that machine. Also, the major drawback to deploy the application using that approach is that the application's dependencies are engaged with the runtime environment. That means the application may be getting crashed when any updates or patches are applied to the base operating system. So then we moved away from bare metal and moved into the idea of virtual machines. And this is where we begin to start virtualizing things. And this basically means we take our actual physical hardware and we are going to use a program called a hypervisor to take that hardware and share it up between the different virtual machines. And each virtual machine will have its own operating system. And on that virtual machine, it will also contain its own libraries and its own version of the application. So this means if you need to scale, you will simply add more virtual machines. And while adding more virtual machines, that's going to be a lot easier than adding more physical servers in general. But it's still not a good solution when you want to deploy things quickly, and that's because it has to deploy the operating system itself as well as the prerequisites required for your application to work properly. And then finally we have our containers. And this is where we start to virtualize not just the hardware, but the operating system itself. So you are going to have your hardware, and of course you are going to have an operating system installed on top of that, just like in bare metal. Or of course there is nothing stopping you from hosting containers on a virtual machine either. And then the container engine platform that sits on top of that operating system is going to leverage the existing kernel of that OS, so the container can run on top of that. Then when the containers are deployed, it has less to deploy. It doesn't have to deploy a full operating system. Instead, it will deploy the application and the prerequisites libraries needed by the application to make it run properly. So those libraries and that application stored in our containers are still fully isolated, and while they can talk to each other, it's going to be as though they were working over a private network, not as though they were two applications sitting on the same server, even they are technically sitting on two containers on the same server. Now let's move on and explain the benefits of container technology. Containers have a lot of benefits when it comes to comparing them to bare metal and virtual machines. Firstly, containers are quicker than virtual machines and bare metal servers. We already mentioned that when we deploy a container, it doesn't have to deploy that full operating system like virtual machines. And of course, you don't have to set up an actual physical server like bare metal. So instead, when you need to deploy something via a container, you can really save a lot of time when you use containers instead of waiting for a VM to provision. Secondly, containers are also very consistent. That means all of the libraries and application requirements are going to be packaged directly in the container. And ideally, when you have an application containerized, all you are going to need to do is share what's called a container image. And that container image is going to contain the application and its prerequisites required to make that application work properly. So once we deploy it, we are not going to have to actually go into the container and do anything. We are just going to have to run that container, and all of that configuration is going to be taken care of for us. Which also means if we share that container image with our friends, then they are going to be getting the exact same application that we have. So that consistency level is going to be really high, and that's going to solve a lot of potential issues that you can get when you hear people saying things like, well, it worked on my computer. Well, with containers, it's going to work on everyone's machine the exact same way. And then finally, deploying containers are simpler than deploying virtual machines. Now we already mentioned that when we deploy containers, these deploys are based on images, and these images contain everything we need. So no need to provision new VM with new OS to deploy our application. So to review, we know that containers are isolated execution environments, which is operating system level virtualization. So while they will contain their own operating system, they will still leverage resources from the underlying one. We know this means that our libraries and our applications will be isolated in a namespace, even if some of our resources are shared, and that containers are faster to deploy and use few resources than more traditional methods such as bare metal or using virtual machines. That's to conclude our session. See you next video. In this video, we are going to talk about container use cases and explain why do we prefer containers over something like virtual machines. Containers can help us solve a lot of common problems that we encounter as administrators or DevOps engineers or developers. These problems such as dev-prod parity and the need to migrate servers. Containers also help us build microservice-based architectures. They can help us create elastic and self-healing architectures, and they just fit with the CI/CD pipelines. Well, let's get started by looking at how containers can help us solve the "it worked on my computer" problem. And this is because when you are deploying using containers, the container running in your production machine is going to be the same container that's running on the developer machine. So if these are based on the same container image, then we can expect the result regardless of the hardware and the operating system used on both production and developer machine. Also, it doesn't matter what libraries they actually have installed on their underlying base operating system, because in the container image we have our application and the prerequisites needed to make that application work properly. So everything is going to be accurate, and again, since we are using the same container image in the dev and the prod environment, then there will not be any disparity. And likewise, this same concept is practical when we are working with migrations. So if we have a containerized infrastructure and we need to move that infrastructure, then all we need to do is lift and shift our containers. And then we can move these containers to new hosts or to new clouds without actually having to change the image or think about what will happen to the image if we take that image and deploy it on Ubuntu machine when it used to be running on real machine. Because again, it's all packaged in the container image, and what's going on in the deployed container is not going to change regardless of the underlying operating system, which means we are also able to redeploy things quicker if we need to migrate. And on the opposite, when we are migrating from a virtual machine to another virtual machine, we have to wait for that full provisioning and configuration management to run. But instead all of that, the container image is already pre-packaged. It just takes that container and it's going to deploy that container without having to wait for a full OS to install and for any provisioning to happen. Of course, containers don't just make deploying things quicker and easier. They can also change how we actually architect our application as a whole. So traditionally, when we built an application, it would tend to be a monolith, which means everything in that application is stored together. So you will have the user interface, and then you will have all of the services packaged in one container. But what if only one of those services, like the database, requires a lot of resources and our database is already packaged with the application as a whole? In this case, when we need to scale up, we are going to have to scale another version of that application. So we are going to have another full application container that's going to contain another copy of the UI and another copy of all of the services that are packaged with it, not just the database. But if you move away from monolithic architecture and instead store each service and UI component in its own container, then you will be able to scale each component individually. So if it's the database and nothing else that really requires more resources, then you are able to add more database containers without having to duplicate services that are working just fine. Using that approach will really save a lot of resources in the long run, because again, you are not making duplicates of services that don't need to be expanded when it's only one component of the application that's really being problematic or needs additional resources. Now moving on, while containers do isolate, containers don't work in isolation. So what does this mean? This means that most often we are using containers within a DevOps context, which means we are using them with other DevOps tools such as orchestration and other monitoring tools that will really help us to manage our deployment. And especially when we integrate the containers with the orchestration and monitoring tools, we can create an elastic architecture. So what does this mean? This means we are going to monitor our containers for CPU, memory, data usage, and other metrics And if we are using too much CPU, or if we are using too much memory, or if our read-write times for our data is getting too slow, then we can scale out. So basically it just means that our monitoring system is going to watch for certain metrics, and if let's say our CPU hits 80% and that metric we denote it as problem, then our monitoring component will notice that, and then it's automatically going to tell the orchestration system to scale out and add another containers so that CPU load can then be distributed among them. And likewise, the orchestration tool can be configured to scale in. So if our CPU usage drops down to 10% on our two containers, so the orchestration system will see that and then remove the additional container to save resources, and then move everyone back on that single 10% CPU container that can handle all the traffic. Likewise, we can also configure the same kind of setup to enable a self-healing architecture. So it's the same concept. You are going to be monitoring your container for when services go offline or when certain errors are received, depending on what your application does. And then once that happens, it's automatically going to terminate that container, so there will not be any need to troubleshoot the container itself. It's just going to get removed, and then it's going to get replaced with another healthy container. Keep in mind that, of course, if there is something wrong with the underlying container image, you are still going to have to go ahead and troubleshoot that image. Then finally, we can leverage containers with the CI/CD, or continuous integration and continuous delivery pipeline as a whole, just because the deployment and the creation of container images and containers in general really fits with the whole CI/CD pipeline concept. And it's the idea of being able to push a change to your application or your code to a centralized repository like GitHub, then automatically have that change detected via your CI/CD pipeline tool such as Jenkins. So something like Jenkins will notice when you make a push to GitHub for your application, and then it can automatically start a build that's going to create a new Docker image based on that change. And if you have it set up to do testing, then it can test that image to make sure it works properly. And then if it passes all of these tests, it can automatically go ahead, take that new version of your application and deploy it to your environment, and this means it will be removing any containers that contain the old version and replacing them with the new ones. So to wrap up, we know that containers fit into a number of workloads and really have a number of use cases and solve a number of common problems we may encounter as engineers, administrators, and developers. And these include solving the dev-prod parity problem, migrating infrastructure, and working with microservice-based architectures, as well as helping us make sure our architectures and our infrastructures always up and running by making them elastic and self-healing. And then, of course, we know that containers can be used with CI/CD pipeline in general. So from here we are going to start learning these concepts and use cases by getting hands-on with Docker, starting by installing Docker in the next lesson. So I'll see you there. As we know so far that containers are portable software package which requires container engine platform to run on top of it. We have many container engines in the market, and the most popular engine is Docker. So in this video I talk about what platforms Docker support, Also, we will talk about our environment which we are going to use in this course, and then we are going to look at how to install Docker Community Edition on CentOS Stream 9. So let's get started. Docker can be installed on a number of platforms. We can install it on Windows via the exe installer found directly on the Docker Hub. We can also install it on Mac, and again that's via a DMG package also found on the Docker Hub, but most properly Docker is installed on Linux. And in this course we are going to install Docker on CentOS Stream version 9. I have provisioned a new fresh virtual machine hosted in VirtualBox. The VM has 4 GB RAM with 2 virtual CPUs and 32 GB storage. And of course this VM should be connected to the internet. Also, CentOS 9 has been installed with the default configuration. So let's move on and see how to install Docker Community Edition on CentOS Stream 9. Before we go and install Docker Community Edition, we need to make sure that any previous version of Docker have been removed from our operating system. And to do that, we use sudo yum remove -y command followed by the list of Docker packages along with associated dependencies. In the output, we can see that there is no previous version of Docker already installed, which is good news. By default, CentOS Stream 9 is coming with Podman as container engine platform. So to avoid any conflict between Podman and Docker, we have to uninstall Podman using sudo yum-y remove command followed by podman run c and build a package. In the output we can see that Podman and its dependencies packages have been removed successfully. Now there is some prerequisite tools we need to go and install. That includes yum-utils, and to do that we use sudo yum install -y command followed by the package name yum-utils. In the output we can see that yum-utils has been installed successfully. After installing our tools, we need to go and set up our Docker repository using sudo yum config manager command followed by --add -repo option followed by the repo URL. This command will create the repo configuration file etc yum repos-d docker-ce repo. Now we are ready to go and install the last version of Docker Community Edition using sudo yum install -y command followed by the package name docker-ce docker-ce-cli containerd.io docker compose plugin. In the output of that command we can see that the installation has been done successfully. After Docker installation is completed, we need to make sure that Docker service will be started during system booting. Also we need to start it now as well. To do that we use sudo systemctl enable --now command followed by the service name docker. To verify we use sudo systemctl status docker command. We will see that the service is up and running and it's enabled. The last thing we need to do is to make sure that Mustafa user is added to Docker group so that Mustafa will be able to run Docker commands as Mustafa rather than using sudo command. And to do that we use sudo usermod -a capital G command followed by the group name Docker followed by the username Mustafa. Now if we run Docker version command using Mustafa user without using sudo, we will see that we have permission denied error, and that's easy to fix. All we need to do just log out and log in again. Let's open new terminal and run docker version command. We will see that the problem is fixed. Now Docker installation has been done successfully. So to summarize, we know that we can install Docker on Windows, Mac or Linux. And if we are going to install Docker on CentOS Stream 9, then all we have to do is remove any existing older version of Docker and also remove Podman package. After that, install the prerequisite packages and add Docker repository. Then just install the packages we need, such as Docker CE, Docker CE CLI, containerd.io, and Docker Compose plugin package. Then start Docker service and enable that service to be running during system booting. And of course, finally, if we want to run Docker without sudo, all we have to do is add the desired user to the Docker group. So that's conclude our session, and in the next lesson we are going to get a high level overview of how Docker works by running our very first Docker container. So see you next video. In this lesson we have Docker installed, so we are going to go ahead and launch our first container, and we are going to do this using the Hello World Docker image. And this image is provided by Docker to test and validate Docker installation. And also we will explain an overview of what's happening in the background when Docker runs. So let's move back to our terminal and see how to deploy our first container. Firstly, keep in mind that Docker environment is managed by Docker command. And if we type Docker command followed by tab key twice, then we will display the list of subcommands which are used with Docker. At any time, if we are getting confused and we need some help, then we simply use Docker command followed by the subcommand such as run as an example, then -- help option. This command will display the documentation of Docker run command. Now to run a container, we simply use Docker run command followed by the image name hello-world. Once this container runs, it will display hello from Docker message. Also, it will display what actually happens when we run Docker command. So let's go ahead and explain what's happening when we execute that command. Firstly, Docker client will contact Docker daemon to say that we want to execute Docker run command to launch this hello world container. Then Docker daemon will try to locate the hello world image on our local computer, and we can define Docker image as a template that contains the application and all the dependencies required to run that application. So Docker daemon will look for that hello world image that we specified, and since it cannot find it locally, it instead will pull the image from Docker Hub. And Docker Hub is a cloud-based repo in which we can store our container images. And now, once this image has been pulled down from Docker repo, then the Docker daemon is going to create a container based on this image. And this is the step that runs the executable that displayed the output message. After running the container, then the Docker daemon will take any output from that executable and send it to the Docker client, which is then going to send it back to us and display it in the terminal. So to summarize, we know we can test our Docker installation by running the Hello World container. And this Hello World container is going to provide us with the high-level overview of how Docker works. Simply, Docker client will send the task we specify in our command to the Docker daemon. After that, the daemon will look for any needed images, and if it's not found it locally, then it will pull the image down from the Docker repository, which is called the Docker Hub. and then it deploys the container based on that image, which then runs the executable or a single command that we have defined to get that container up and running. So now that we have Docker set up and we know an overview of how it works, then in our next section we are going to start learning how to actually manage and work with containers throughout their life cycle. So see you next video. In our previous lesson we launched our first container, but there is a little bit more to launching containers than we just demonstrated. So in this lesson we are going to go ahead and we are going to explore the various ways that we can actually set our containers to launch. So we are going to take a look at general launching and listing. We are going to look at how we can launch and immediately interact with our containers, as well as how we can launch and have our container run persistently in the background. And then we will explore how we can work with both temporary containers and more persistent containers that will start if our server shuts down automatically. And then finally, of course, we will have our end of lesson wrap up. So let's get started and go ahead and access our terminal. So in our last lesson we launched a container using docker run hello world, and we saw that container automatically output some information for us about how Docker works. But what happened to that container afterwards? Is that container still running? Well, we can check the running containers by using docker container ls command, and in the output of that command we can see that we actually don't have any running containers, and maybe that behavior is exclusive to the hello world container. So let's run something else. Let's do a docker run alpine to run another container using alpine image, which is a very small Linux distro. And let's see what happens, and it's going to pull down the alpine image from the docker hub. But now what happens if we do docker container ls command again to see what containers we have running? We will see that there is still no containers there. So what's going on there? Now when we launch a container with a docker run command, then the containers set to run one specific command, and once that command is done it will exit the container and the container will enter a stopped state. So when we run our hello world container, that initial command that's run is the command that sent us the output we saw that describes how Docker works. So if we want to list all containers including the stopped containers, then we use docker container ls-a command, and then we can see that we have two containers, the alpine container that we launched, and then we also have that hello world container. Also notice here that we can see some useful information such as the container ID, the image from which this container is running, the initial command which is executed when the container runs. Also we can see the age of the container and its status. Plus we can see the ports of the container which can be used to access the container through the network. And finally we can see the container name generated randomly by Docker. So what happens if we want to run a container and we don't want it to exit immediately, and instead of starting our container running a command, we want to actually access the command line of that container? In this case, we can use docker run command with some flags such as -i for interactive and -t to open TTY terminal inside the container. And also we want to assign a specific name for our container. For that we use --name option followed by the name such as demo_1. And then finally we define the image name Alpine, which is a small Linux distro image. Now when we run this command, it's going to open a shell inside our container called demo_1, and that container has been created from Alpine image. So of course from here we can interact with our container like any server. So if I want to upgrade the server, then I can run apk upgrade command, and apk is just the package manager for Alpine. Then what will happen if we exit this container using exit command? And let's go ahead and do docker container ls again to list the running containers. Of course we will see that the container is stopped. So what happens if we want to run a persistent container? Let's say we have a container that contains a web application that we need it up and running all the time. Well, in this case we can leverage the -t flag again, but this time we are going to pair it with -d, which will set the container to detach or run in the background. And the -t will ensure that it has a persistent IP address and everything we need for that container to persist. Also, if we need that container to be running automatically during system boot, we use --restart option followed by always flag and --name option to assign a name for our container as bg_container. And finally the image name Alpine, from which this container will be running. In the output of that command we can see that's our container ID, which has been generated for our container. If we run docker container ls command to list the running containers, then we will see that bg_container is still up and running. So to review, in this lesson we learned a variety of ways to launch containers, including just your regular docker run, but we also learned how to pair that with the -i-t flag to ensure we can drop into a working shell. We learned how to make sure the container runs in the background with -d, and then of course we also learned how to make sure our container always restarts when our overall host server shut down or something happened to our container. And then finally we learned how to provide our containers with nicknames so we can work with them easier and not have to deal with the randomized generated names that Docker provides for us. That's conclude our lesson. See you next video. At this point we explained how to launch a number of containers, but how can we actually access and work with these containers if we need to change anything inside the container itself? So in this lesson we are going to learn how to start one of our many stopped containers, and we are going to look at how we can run commands on a running containers, as well as how to directly access a shell on our containers, before finally learning how to copy files and then going through our normal lesson wrap up. So let's get started by jumping on our terminal. At this point, if we run docker container ls-a, we will see that we have a number of containers that have been started and stopped, but only one of them is actually up and running, which is bg_container from the previous lesson. So let's say we want to start one of our stopped containers. And to do that, we just have to run docker start command and then define the name of the container we want to work with. And in this case, let's work with our demo_1 container. So now if we run docker container ls, we can see that we have our bg_ container and our demo_1 containers both up and running. So what if we want to actually work directly on the container? Let's say we want to add Nginx to that demo_1 container. Well, in this case, we can use docker exec command followed by the container name demo_1, and after that we just have to specify the command we want to run inside the container. So we can do apk add nginx to install nginx on our container. Alternatively, perhaps we have a number of commands to run and we don't want to define a docker exec each time. So in that case, we can actually drop directly into our container's shell by using docker exec-it command followed by the container name demo_1 and then the default shell used by Alpine Image, which is ash shell. Keep in mind that if we are using Ubuntu or CentOS image, then we have to specify bash shell as a default shell. So that command will drop us inside demo_1 container using its default ash shell. And from here we can run any commands normally. So if we want to ensure that Nginx is installed, then we can take a look at /etc/nginx directory using ls command. Of course, if we need to actually modify the content of the container, then it's probably not enough to simply access the container's shell. Instead, you may need to actually upload and download files, and for this we have the option to use docker cp command. So let's say we need to copy /home/mustafa/test1.txt file from our local host to the demo_1 container. In this case, we use docker cp command followed by the source file /home/mustafa/test1.txt located on my local host followed by the destination as the container name demo_1, then colon, then the destination inside the container like /temp. So that command will copy the file test1.txt from /home/mustafa on the local host to /temp inside demo_1 container. And to verify, we can use docker exec command followed by the container name demo_1, then ls/temp. This command will list the content of /temp inside demo_1 container. Here we can see that test1.txt is there. Likewise, we can use the same concept to copy files from the container to the local host using docker cp command followed by the container name demo_1, then colon, then the source file location inside the container /temp/test2.txt, then the destination on the local host /home/mustafa. So that command will copy or download /temp/test2.txt file from demo_1 container to the local host on /home/mustafa directory. So at this point, we know how to start a container that has been stopped or exited. We know how to run a command against a container, as well as how to drop into the desired shell if we want to work with the container directly. And finally, we also learned how to copy files to and from our containers as needed, so we can configure our container properly. Now you may have noticed that we have a lot of containers to work with at this point. So in our next lesson, we are going to take a look at how we can manage these containers both individually and as a whole to make sure that our overall Docker environment is clean and it contains only what we need, and also to make sure that our containers are performing as expected. So let's see you on the next video. At this point, while we have two containers up and running, and I am sure you know that we have a number of stopped and exited containers, so in this lesson we are going to look at how we can manage our containers so our environment will contain only what we need. So we are going to do this by taking a look at how we can stop and start containers, which we have touched on a little bit already. We are going to look at how we can remove unimportant containers as well as how to rename containers. Then we will explain how to view container metrics, and then finally we will wrap up everything as usual. So let's get started by opening our terminal. Now if we do docker container ls, we know we have our bg underscore container and our demo underscore one containers are both up and running. But at this moment we really only want to keep our demo underscore one container because that's the container that we are going to keep working on. So in this case we are going to start this lesson by stopping our bg underscore container using docker stop command followed by the container name bg underscore container. To verify, we use docker container ls command to list the running containers, and in the output of that command we can see that we have only demo underscore one container up and running, which means we are now good to go ahead and remove any of the containers that we don't need. So if we know that we don't need our bg underscore container, so we can remove that container using docker container rm command followed by the container name bg underscore container. And to verify, we use docker container ls-a, we will see that bg underscore container is deleted. In case we have many stopped and exited containers and we need to delete all of them, in this case we can use docker container prone command. And since that command will delete all of the stopped containers, then it's recommended to make sure that all of your stopped containers are the ones you don't want by using docker container ls-a command to list all the containers including the running and stopped ones. Once we run docker container prone command, it will give us this lovely warning to confirm that we are going to delete all the stopped containers, and since that we need, we will type a y and then enter. Now to verify, let's run docker container ls-a command. We will see that all the stopped containers have been deleted and we have only demo underscore one container which is up and running. And now from here we are going to be almost exclusively working with our demo underscore one container, but we most likely want to give this a little bit of a better name. For example, we know that we are installing Nginx on that container, so it seems like a web container, so let's call it web1 instead of demo underscore one. And to do that we use docker rename command followed by the old name demo underscore one, then the new name web1. Now to verify, we use docker container ls, and in the output we can see that our container has a brand new name, but nothing else has been changed. It still has the same container ID, and it's still created many days ago, and it's still up the same amount of time. Now, as long as our containers are up and running, we will need to know some information about these containers. And while of course you can set up an entire monitoring tool like Prometheus or Zabbix, also Docker provides some simpler ways just to check our CPU memory and process information, and we can do this by running docker states command. That command is going to return information for all of our running containers, including the container ID, the container name, the CPU usage, the memory usage, plus the network and the block ID information. This useful information can help us troubleshoot and manage our containers. And to exit from this command, just press Ctrl C. If we are interested in getting the same information for a specific container, then we can use the same command docker states followed by the container name web1. So again, to review, we learned how to start and stop our containers with a docker start and stop command. We can also restart containers with docker restart command. And we learned how to remove a container with docker rm, as well as remove all stopped containers using the docker container prone command. And then of course we also learned how to rename containers using docker rename command. Then finally we learned how to get and view statistics for our running containers using docker states command. So at this point we now have an almost fully configured web container that we can use to launch a website. So in our next lesson we are going to figure out how to do just that, and then make sure that website is available not just on our container but also to the general public through the IP address of our local host. So see you next video. In this lesson we are going to explain how we can use container to publish a website and access it locally and from the external network. Because when we deploy an application or any sort of microservices on a container, we need this application to be accessible not only from the local host, but rather we need this application to be accessible from the external network. So in this lesson we are going to take a moment to learn how we can discover certain information about our container, like the container IP address. Then we are going to look at how we can copy a container to create a new image, so we can reuse it and then take that new container and map it to a port on our local host. Then finally we will wrap up everything we have just learned as usual. So let's get started by jumping onto our terminal. So at this point we have our web1 container up and running, and the expectation is it's going to be a web server serving some web content. At the beginning we will create the default configuration file for Nginx called default.conf, with that content including the default web content location as user share nginx html. Then we will use docker cp command to copy that default.conf from our local host to etc nginx http.d directory inside web1 container. And in order to have our web1 container serve a website, we need to provide it with some content to serve. For that we are going to do this by generating our own index.html page, and we will keep it simple with that content. After that, let's create the default web content directory for Nginx inside web1 container using docker exec command followed by the container name web1, then mkdir user share nginx html. So that command will create user share nginx html directory inside web1 container, and that directory is the default location for the web content for Nginx. Then we will copy index.html file from our local host to /user/share/nginx/html directory inside web1 container by using docker cp command. After uploading the index.html file to the web content location inside the container, Then we are going to start nginx process using docker exec-dt command followed by the container name web1, then nginx-g command to run nginx process inside the container, and it needs to define the location of the process ID as pid/temp/nginx.pid. Then we also want to make sure that this will not be running as a daemon, so we are going to set it as daemon off. Keep in mind that this is how to start nginx process inside the Alpine image. So in case we use CentOS image, then we will use another command. Now we need to make sure that we can access the website that we have deployed, and to do that we will need to get the IP address of the web1 container. We can do that using docker inspect command followed by the container name web1. In the output of that command we can see a lot of information related to our container, including the IP address of that container, which is 172.17.0.3. Now to make sure that our nginx setup is working, we can just go ahead and we can clear that IP address. Here we can see that our website is working properly. So now that we know our website is working, we still have one problem. Everyone that's on this actual physical host will be able to access our container. I mean that we can access our website locally from our local host. But what if we want to publish our container to the world so that anyone can access the website from the internet? So to access the website from the internet, we will need to do something called port mapping, which means we will map a port on our host to a port inside the container. But before doing that, let's create a new image from the running container web1 to use the same nginx configuration. And to do that, we use docker commit command followed by the container name web1, then the image name webbase. So that command will create an image called webbase from the running container web1. That means the webbase image will contain the index.html and default.conf files we have just created. Then from that webbase image, we can go ahead and launch a new container called web2 using docker run command followed by -p option to map our ports. So now it's port 80 on our local host that we want to map to port 80 inside our container. Then -dt to make sure that our container launches in the background. Then --name to provide a name for our container as web2, and then of course we are launching this from our webbase image. Now let's go ahead and start nginx process using docker exec-dt command followed by the container name web2, then nginx-g command to run nginx process inside the container. And it needs to define the location of the process ID as pid/temp/nginx.pid. Then we also want to make sure that this will not be running as a daemon, so we are going to set it as daemon off. Now let's get the IP address of our web2 container using docker inspect web2 command. We will see it's 172.17.0.2. To verify that our website is working properly, we can curl using the container IP address. We will see that we can access our website from the local host. Now we need to ensure that we can access the website from the external network using the IP address of the local host. And to do that, let's get the IP address of our local host using IPA command. We will see the IP address is 192.168.1.50. Finally, if we open Chrome and try to access the website using the host IP address, we will see that it's working as expected. So in this lesson, we learned how we can share our container content with the internet by making sure that we can grab our container information via the docker inspect command. Then we learned how to make an image from an existing running container using docker commit command. So we can go ahead and launch a container that's mapped to a port on our host using docker run-p command. So in our next section, we are going to get more hands-on with images management and learn how to actually make an image using a docker file from scratch. So see you next video. At this point, we know that applications can run inside containers as a way to provide them with an isolated and controlled execution environment. Running a containerized application means running an application inside a container, and that requires a container image, which is a file system bundle, provide all application files, libraries, and dependencies that the application needs to run. In other words, container image is the source of our containers. So in this lesson, we are going to learn how to manage the image through its life cycle. We are going to explain how to search for an image and pull down this image. Then we will learn how to delete old images, and finally we will go ahead and explain image tagging concept before wrap up everything we have just learned. So let's get started by jumping onto our terminal. As we know so far that these container images are stored in online registries such as Docker Hub, which allow users to search and retrieve container images. Docker users can use the search subcommand to find available images from the remote or local registry by using Docker search command followed by the image name like Nginx. So that command will search for Nginx image in the Docker Hub online registry and display the available Nginx images with some useful information such as the image name along with short description about that image. Also, we can see the Nginx official image maintained by Docker Hub, and we can see another Nginx images maintained by other users such as Ubuntu/Nginx image, which maintained by Ubuntu. After finding the image, we can use Docker to download that image. When using the pull subcommand, Docker will fetch the image and save it locally for future use. So Docker pull Nginx command will download the latest official version of Nginx created and maintained by Docker. In case we need a specific version of Nginx maintained by another user like Ubuntu, then in this case we have to specify the username then / the image name, such as docker pull ubuntu/nginx. After downloading the image, Docker will store the images locally and we can list them with the docker images command. In the output of that command, we can see the image name, the image tag which defines the image version, the image unique ID, and when the image has been created, and finally the image size. Keep in mind that any container image downloaded from a registry is stored locally, and this behavior avoids repeating image downloads and minimizes the deployment time for a container. Docker also stores any custom container images you build in the same local storage. Any image has a tag which defines the image version. So the image tag is a mechanism to support multiple releases for the same image. This feature is useful when multiple versions of the same software are provided, such as a production-ready container or the latest updates of the same software developed for community evaluation. And if the image name doesn't contain a tag, then the tag value defaults to the latest version. So if we need to download or use a specific image version, then we have to specify the tag in the command. For example, docker pull command followed by the image name MySQL, then colon, then define the image tag as 5.6. So that command will download MySQL image version 5.6. And to verify, we use docker image command to list the downloaded images on the local host. We will see that MySQL 5.6 image has been downloaded. Images can become outdated and should be subsequently replaced, and any updates to the image in the online registry is not automatically updated on the local image. So the image must be removed and then pulled again to guarantee that the local storage has the latest version of the image. So to delete the image, it's recommended to stop and delete its container first, then delete that image. So firstly, let's list the running containers using docker container ls command. We will see that we have two containers are up and running, web 1 and web 2. So to delete the web base image, we have to stop its web 2 container using docker stop command followed by the container name web 2. Then delete web 2 container using docker rm command followed by the container name web 2. Now web 2 container has been deleted, which means its web base image is ready to delete. So to delete the image, just run docker rmi command followed by the image name web base. And to verify, use docker images command. We will see that web base image has been deleted. When working with docker images, we should be familiar with the concept of image tagging, which defines the image version. Usually, the tags are used by container developers to define multiple versions of the same software. So multiple tags are provided to identify a release easily. To add a tag to specific image, simply use docker tag command followed by the source image MySQL, then colon, then the current tag 5.6, then the new image name MySQL, then colon, then the new tag custom tag. To verify, we use docker images command. We will see that the same image ID has two tags. The first one is the default 5.6 tag, and the second one is the new custom tag. That means we can consider tags as they are aliases to the ID of the image. As we know that single image can have multiple tags assigned using the docker tag command, and to remove these tags, simply use docker rmi command followed by the image name MySQL associated with its custom tag. To verify, use docker images command. We will see that MySQL custom image has been deleted. So in this lesson, we learned how to search for a specific container image using docker search command, and how to download that image using docker pull command. Then we learned how to delete the container image using docker rmi command after cleaning up its containers using docker stop and docker rm command. Then finally, we learned how to tag images using docker tag command. In the next video, we are going to learn the best practice of how to create docker custom images using docker file. So see you next video. In the previous lessons, we explained one method of creating container images, which includes create the container, then modify that container to meet the requirements of the applications to run in it, and then commit the changes to a new image. This option is straightforward, and it's a good option for using or testing very specific changes. but it doesn't follow best software practices like maintainability, automation of building, and repeatability. So ideally, all container images should be built using a Docker file in order to create a clean and lightweight set of image layers without log files, temporary files, or other artifacts created by the container customization. So the Docker file is a mechanism to automate the building of the container images. Now let's jump onto our terminal and see how to create a Docker image using Docker file. Firstly, we will use mkdir command to create a working directory called Linux. This directory will contain all files needed to build the image, and creating an empty working directory is the best practice to avoid incorporating unnecessary files into the image. Also, for security reasons, the root directory / should never be used as a working directory for image builds. Then use your preferred editor and create a new Docker file with capital D inside the working directory. As we can see, that's a text file that contains the instructions needed to build the image. Lines that begin with a hash are considered as comments. The comments inside Docker file consists of two parts. The first part is the instructions, which are not case sensitive, but the convention is to make instructions all uppercase to improve visibility. And the second part is the argument. Keep in mind that Docker file instructions will be executed in sequence. Now let's move on and explain the Docker file content in more details. The from instruction defines that the new container image will be created from the latest version of fscm/CentOS container base image, which means this CentOS image will be used as a parent for our custom image. Below the from instruction, add the maintainer instruction to set the information about the image creator, such as his name and his email. Then below the maintainer instruction, add the label instruction to add short description about the new image. After that, add run instruction with a DNF update command to update the container OS and DNF install command to install Apache on the new container. Then add run instruction to replace the contents of the default HTTPD home page using echo command. After that, use the expose instruction below the run instruction to define the port that the container will listen to when the container is running. In this instance, set the port to 80 because it's the default for Apache server. Finally, use the entry point instruction to set HTTPD as the default entry point that defines the initial command which will be executed when the container is running. Now let's save and exit the file. After creating the Docker file, we are ready to build our custom image, and to do that we use docker build command followed by -t option to define the name of the new image as http-custom, then colon, then define the tag for this image as v1.0, then dot, which defines the current working directory which contains the Docker file. In the output of that command, we can see that each instruction in the Docker file creates a new image layer, which means having too many instructions in a Docker file will create too many layers, and as a result that will create large images. Now docker build command has been done successfully. If we use docker images command to list the local images, we will see that http-custom image has been created with v1.0 tag. Also, we can see the parent CentOS image from which our http custom image has been created. Now let's run a container from our custom image using docker run command followed by -d option to run the container in the background, then -p option to expose the container internal port 80 to the port 8080 on the local host, then the image name http-custom:v1.0. And to verify, let's curl on the loopback address 127.0.0.1:8080. We will see that our website is working as expected. That's conclude our session. See you next video. Container storage is considered as ephemeral storage, and that means its contents are not preserved after the container is removed. So containerized applications work on the assumption that they start with empty storage, and this makes creating and destroying containers very simple operations. Ephemeral container storage is not sufficient for applications that need to keep data over restarts, such as databases. To support these applications, we must provide a container with a persistent storage. So in this lesson, we are going to explain two different methods for how to create a persistent storage for our containers and how to remove these volumes before wrap up everything we have just learned. So let's get started. We have two methods to create a persistent storage for our containers. The first method is that we can create and manage volumes outside the scope of any containers using docker volume create command followed by the volume name myvol. This command will create a persistent storage volume called myvol. Once we create the volume, Docker will create a dedicated directory for that volume with the same volume name in /var/lib/docker/volumes directory. And to list the current volumes, we use docker volume ls command. In the output of that command, we can see that the volume myvol has been created. Also, we can get more information about the volumes using docker volume inspect command followed by the volume name myvol. We will see that myvol volume is mounted locally on the /var/lib/docker/volumes/myvol/_data directory. Also, we can see when this volume has been created. To delete the volume, we use docker volume rm command followed by the volume name myvol. The second method to create the volume is by using docker run command. So if we start a container with a volume that does not exist, then Docker will create that volume for us. For example, we use docker run command with --mount option to mount the volume myvol2 as a source into /app directory as a target inside the dev test container created from nginx image. To verify, we use docker inspect command followed by the container name dev test. This command will display very useful information about dev test container. And if we go to the mounted section, we will see the volume name myvol2 and the source, which defines the directory of the volume in the local file system as /var/lib/docker/volumes/myvol2/_data. Also, we can see the destination inside the container as /app. And finally, we can see the permission of the volume as read and write. So that means the volume is created and mounted correctly. Let's create a file in /app directory inside dev test container using docker exec command followed by the container name dev test, then touch command to create a file test1. And if we list the content of the volume inside the local file system, we will see that test1 file is there. Now if we stop the dev test container using docker stop command, then remove that container using docker rm command we will see that we still have the file test1 in the volume myvol2, which means the original content is still accessible even if its container has been deleted. So in this lesson we explained how to create Docker volumes using Docker volume create command and how to remove these volumes using Docker volume rm command. And then finally we learned how to create these volumes when running the containers using Docker run command. That concludes our session. See you next video.